Okay, here we go. Lesson number 2 from covering chapter 5 of three lessons that will cover all of chapter 5. As you can tell, that means there's a lot crammed into each one. These are really just overviews. Let me stress once again, where I just show you all the main ideas in the chapter. Just so you get a sense for what's there, and then you really need to go do the practice questions to really master it. So very quickly, Math 038 and 052, this particular lesson does not directly impact you. Anything you need to know about powers was at the start of the first lesson. Anything you know about roots will be at the start of the third lesson. Math 053, this is all about finishing it. Once we do this, we'll have done all the exponent sections, 5.1, 5.2, and 5.3, and again, an overview. There's no possible way we can cover every possible variation of question. We have 5 or 6 or 7 exponent laws, depending how you look at it. And there they are. I got them listed as 6 here. And then what's going to happen is after you practice each one individually, they're going to put them all together. And you have the combinations and variations in questions are limitless. So you have to know each law and then be able to apply them in order. So we did those 4 in our last lesson. We're going to do these 2 right now, and then just talk a little bit more about another concept at the end called scientific notation to finish off the section. So first one, easy. Anything raised to the power of 0, this is a bit of a shocker, is equal to 1. You would have thought it was equal to 0. 0, I know, but actually it's equal to 1. Let me show you why. And again, let me stress that you do not need to know the why. Don't try and frantically copy down the steps on the why. I'm just showing you quickly why this is true, and then we'll do a couple practice questions. So let's think of 2 to the power of 4 over 2 to the power of 4, and we're going to evaluate this a few different ways, none of which you'd actually do if you got this question on a test. I just want to show you why this is true. So we could evaluate the top and the bottom separately and then divide them. So on the top, we have 2 to the 4, which is 2 times 2 times 2 times 2, or on your calculator, you'll get 16, 2 to the power of 4 using your power button. On the bottom, we also have 2 to the power of 4, which evaluates to 16. And now we see that this is 16 divided by 16. Well, 16 divided by 16 is 1. Perfect. Let's try it a different way. We could have also expanded those exponents and canceled them. So 2 to the power of 4 is 2 times 2 times 2 times 2. Same thing on the bottom. And now we see that those guys cancel, leaving 1 and 1. So do those, so do those, so do those. So everything cancels. We have a bunch of 1s on the top and a bunch of 1s on the bottom. 1 divided by 1. We see a separate method which also shows that this answer is 1. Now let's look at a third one using exponent laws. 2 to the power of 4 divided by 2 to the power of 4. We saw last time that when you divide with the same base, you subtract the exponents. So that is 2 to the power of 4 minus 4. And of course, 4 minus 4 is 0. And right there you have our rationale for why something raised to the power of 0 is equal to 1, because here we evaluated this using exponent laws and we found that it's equal to 2 to the 0. But in the other 2 ways that we worked it out, we discovered it's equal to 1. So therefore, 2 to the power of 0 must be equal to 1. And I could have done the same thing with any other number to the power of 0. So there is our next law. Now here we're going to do some practice on these. This is the easiest practice questions you'll ever see, because anything raised to the power of 0 is 1. So here we have 175 raised to the power of 0. That's 1. Here we have a variable. That's okay. Raised to the power of 0. It's 1. Here they have the nasty ones when math teachers are sitting up late at night dreaming up really, really mean questions, because you might spend 10 minutes trying to evaluate all this stuff in the middle and work it all out, just to notice afterwards that it's all then raised to the power of 0, which means it's 1. You don't need to do any of that work, right? Same thing on this one. Last time we learned to multiply monomials, so you could go 8 times 3 and x squared times x cubed and y to the 5th times y to the 7th, and work all that out, and then you say, oh, then it's all raised to the power of 0. I didn't need to do any of that. It's equal to 1. Like I said, the easiest set of practice questions you'll ever have. Anything raised to the power of 0 is equal to 1. Okay, we're going to go back to division because we know that we subtract the exponents when we divide with the same base. So there's 7 to the 14th divided by 7 to the 9th. You see we have our weird instructions: simplify but do not evaluate, which is you're not going to run into very often. We know we subtract 14 minus 9 if we're dividing with the same base. 14 minus 9 is 5. So this is equal to 7 to the power of 5. Now, in all of the questions we've done so far, they have been like this one, where the exponent on the top is bigger than the exponent on the bottom, so we get a positive number here. What happens if the exponent on the bottom is bigger? Like 5 to the 4th over 5 to the 7th. And again, we're going to do this 2 different ways. I think we might just do it one way first and do some practice, then do it the other way. So again, this is not how you want to do the question. This is just me showing you what the result is. So 5 to the 4th on the top is 5 times 5 times 5 times 5. 5 to the 7th on the bottom is 7 5s. This is feeling familiar. A bunch of those 5s cancel out, leaving behind 3 5s, this time on the bottom. So the top is just 1. 1 times 1 times 1 times 1. The bottom is 5 times 5 times 5, which is 5 cubed. So we see that just like before, we subtract, but if the exponent on the bottom is bigger, one way to think about it is that you still subtract, but your answer goes on the bottom instead of the top. So if we had 5 to the 7th on the top and 5 to the 4th on the bottom, we would get 5 to the 7 minus 4 is 5 cubed. But we actually have 5 to the 7th on the bottom. We still subtracted 7 minus 4, but since the bottom exponent is bigger, our answer goes on the bottom. This is probably how you want to do what I just described, subtracting 7 minus 4 and putting it on the bottom, is how you want to do these questions when they come up. When the exponent on the bottom is bigger, we still subtract. Our answer goes on the bottom. So taking a look here, I got several examples. So we're dividing with the same base. So we know we subtract the exponents, but in this case, the bottom one is bigger. So I still go 26 minus 12, but there's more q's on the bottom. All the q's on the top cancel out, all 12 of them, leaving behind 14 q's on the bottom. Same thing with the second one. 7 to the 19 over 7 to the 21. We're dividing with the same base, but there's more 7s on the bottom than the top, so we still subtract. Okay, so 7 to the 21 and 7 to the 19, we're dividing with the same base. We subtract, but since there's more on the bottom, 21 minus 19 is 7 squared. And wait a minute, it says simplify. It doesn't say do not evaluate. So here, q to the 14, that's all I can do. 7 squared, I can carry on and turn that into a number, right? 1 over 49. How about here? We got some j's, we got some k's. Let's see, there's more k's on the top and more j's on the bottom, but we're all dividing with the same base, right? We're also multiplying the top, a j and a k, to the 5th and 11th, but we can't do anything if the bases aren't the same. So let's separate those out. Let's look at the j's first. Do I do the j's first? I do, yeah. Dividing with the same base, so we subtract, but there's more on the bottom, so that's where it goes. That's where the leftovers will be. K to the 11 over k to the 3 will be k to the 11 minus 3. And then you just do those subtractions. And again, you can think of this that way, or you can also think of this as all five of these j's on the top canceled out, leaving behind 5 on the bottom, right? All 11 of these k's being multiplied up top and then there's 3 k's being multiplied on the bottom. All 3 of the ones in the bottom cancel, with 3 of the ones from the top leaving behind 8 k's being multiplied on the top. You give that one a try. Okay, so you can see I've color-coded for you there. There's a 20 and a 15. Those are just regular old numbers. That's like a fraction. Just ignore everything else. That's like the fraction 20 over 15. That can be reduced. They both divide by 5, giving 4 over 3 for the number part. Now for the power part. We have 15 m's multiplied on the top and 4 on the bottom. That is going to leave behind 11 on the top, or 15 minus 4. We have more n's on the bottom than the top, so that's going to leave behind some on the bottom. 15 minus 4 is 11. 10 minus 8 is 2. Again, I'm showing it here with the subtraction. I personally don't think of it that way. I think of 4 m's on the bottom cancel out 4 out of the 15 on the top, leaving behind 11. The 8 n's on the top cancel out 8 of the 10 on the bottom, leaving behind n squared, 2 n's being multiplied. Okay, now that is one way to think about when the exponent on the bottom is bigger. And again, that is the best way when you get questions like this that ask you to simplify. We are going to look at this same setup that we used before in a different way to discover what we can learn about an exponent that is negative, because here we worked out that 5 to the 4th over 5 to the 7th is 1 over 5 cubed, right? Based on the canceling method we did. Oh, so my red lines are all off there. Sorry about that. We could have also done this. We could have said, oh, you're dividing with the same base. Subtract the exponents. What's 4 minus 7? Negative 3. So over here, we recognized that the leftovers were going to be on the bottom, so we put them here. Here, we just pretended we didn't know that, and we just did the straight-up rule, 4 minus 7, and we get a negative. So what we discover is that a negative exponent actually means the thing is on the bottom. 5 to the power of negative 3 is 1 over 5 to the power of positive 3. So there is all, we've covered all the rules. We're going to do some practice still on this last one, but we've now explained all 6 of those rules that you're going to be making use of. And the trick is going to be applying them. And again, as they mix them up on you, they put multiple ones in the same question. So let's try some of these with our negative exponents. Let me just reemphasize one more time. Don't create negative exponents unless they want you to. So here, we could have taken all these and made negative exponents, but we don't want to unless we absolutely need to, unless they tell us, give your answer with a negative exponent. So negative exponents are something we're usually trying to get rid of, not create. So when you see these questions, just say, oh, all the leftovers are on the bottom, right? That's a way easier way to think about that. Only when they give you negative exponents in the questions, then you're going to have to use that rule. So 6 to the power of negative 5. Our new rule says that is 1 over 6 to the power of positive 5. And let's see, well, that's something we can evaluate. They didn't tell us not to evaluate, so on your calculator, 6 to the power of 5, you should get 7,776, apparently. How about this one here? We have a power raised to another power. Well, let's multiply the powers. 5 times negative 4. So that gives us y to the power of negative 20. And what is a negative exponent? Y to the negative 20 is 1 over y to the positive 20, like so. How about this one? You know what, I'm going to let you try these two. So this is a multiplying with the same base. So you're going to add the exponents and then figure out what to do from there. This one is dividing with the same base, so you're going to subtract the exponents. I'm going to give you a minute to give those a try. Okay, so we're multiplying with the same base, so we know that we add the exponents. 3 plus negative 7. that we can add those together. That adds up to -4. And we don't like negative exponents in our answers, like I said, unless they specifically tell you they want it, which they don't do very often. So t to the -4 is 1 over t to the +4. And the last one, we're dividing with the same base, so we subtract the exponents. 5 minus -2. Minus a negative, you remember, becomes plus. So it's actually 5 plus 2, which is 3 to the power of 7. This one we actually can evaluate because it's actually a number, so we do, unless they specifically told us not to evaluate, right? We simplify means simplify as far as you can, including turning it into an actual number if possible. So there's some examples of what you do when you are given a negative exponent. Let me emphasize again, do not create negative exponents as a generally as a rule. I'm sure there's exceptions because there's exceptions to everything, but in general you don't want to take a situation that doesn't have negative exponents and make negative exponents in there. So you want to use that exponent law to get rid of negative exponents. Now I'd like to look at this last part D there a little closer, because something interesting happened there that helps us expand on this rule. Look at what happened with that negative exponent on the bottom. Look at all the other questions. They have a negative exponent on the top, right? This one has a negative exponent on the bottom of the fraction. And look what happened to that -2 on the bottom. It became a +2 on the top. So just in the same way that a negative exponent on the top becomes a positive on the bottom, the exact opposite happens. A negative on the bottom becomes a positive on the top. So again, look back at these questions. 6 to the -5, right? That's on top because the 6 is over 1, even if we don't write it, became 1 over 6 to the +5. A negative exponent on top became a positive exponent on the bottom. We now have discovered that a negative exponent on the bottom becomes a positive exponent on the top. So let's look at a couple examples here. 1 over x to the -5. Don't need to get all fancy. 1 over x to the -5 becomes x on the top now. X over 1 if you really want to get technical, but we don't bother to write it, right? So a negative exponent on the bottom becomes a positive exponent on the top. 1 over x to the -5 is x to the +5. Here we have negative exponents on the bottom and the top, so the one that's on the top is going to go to the bottom as a positive, and the one that's on the bottom is going to go to the top as a positive. So a to the -3 becomes 1 over a to the +3, and b to the -8 on the bottom becomes b to the +8 on the top. So a nice nifty little pattern that works both ways, right? A negative exponent on top becomes a positive exponent on the bottom and vice versa. Now looking at this, we could take that -3 exponent into both the top and the bottom and then do it the same way we did this question. Or we can be like, oh hey, what's that negative exponent going to do? It's going to make the tops go to the bottom and the bottoms go to the top. So that becomes 3 over 2 to the +3. And if you want to, this is actually the technical way to describe the negative exponent rule. Something to a negative exponent becomes the reciprocal to a positive exponent. And if you look at all these other examples we did, that same language applies, right? Because, again, I'm going to go back. 6 to the -5. What's the reciprocal of 6? It's 1 over 6. So 6 to the -5 is its reciprocal, 1 over 6 to the +5. If you're wondering why the 1 isn't raised to the 5, well, it is, but 1 to the 5 is just 1, so we don't need to write it. I wouldn't think about it that way, but just so you see that language works in all examples. So if you have negative exponents on the top, they become positive on the bottom. If you have negative exponents on the bottom, they become positive on the top. If you have a fraction to a negative exponent, same thing, the tops and bottoms switch places and the exponent becomes positive. We can now work this out. 3 cubed on the top, 2 cubed on the bottom, which is 3 times 3 times 3, 27, 2 times 2 times 2, 8, or use your power button, whichever you find easier when it's just a power of 3. Okay, so what you're starting to see probably is that, look at these last examples, those ones and these ones, especially here, we started mixing together exponent laws. Here we had multiplying with the same base, so we add, and then we got a negative, right? For example. So you're going to find that as they mix together, the, these different laws coming up in the same question, things get more and more complicated. You really need to do the practice. Just seeing me demonstrate each of these rules helps you understand the rules, but then you need to practice applying them. So we're just going to do one kind of more complicated example just so you get the idea of what can happen. But again, we can't go through every possible scenario. So here I have, let's see, I have a fraction raised to a negative exponent. There's a couple things to do. You could do first. That's the other thing I should point out. There's not necessarily a right or wrong way to do it. You can go in different methods depending on what looks like it's going to work better for you. And some might be faster or slower. But as long as you're following the laws, then you're going to get the same answer. So here, what I would do, I think, if I look at this, is I would look at that fraction and see that things can cancel out in there, and I would reduce that. So, um, yeah. So what I think I would be tempted to do is to look at the 12 over the 18 and the x cubed over x to the 8th and do some simplifying. 12 and 18 can both be divided by 6. So that gives 2 over 3. And let's see, we're dividing with the same base. So subtract the exponents, but there's more on the bottom, not the top. So the leftovers are going to be on the bottom, right? There's 3 x's on the top being multiplied. There's 8 on the bottom. 3 out of those 8 cancel, leaving 5 behind. Could have I also turned that into an x to the negative 5 on the top? Yes, I could have, right? X to the 3 minus 8 on the top. And what would happen to that x to the negative 5 on the top? It would become an x to the positive 5 on the bottom. So you can see there's more than one way to go. There's just some that are faster and some that are slower, as long as you're applying the laws and following the rules of math. So this is what I would say is the easiest. There's another thing we could have done first too. We could have said, oh, hey, a negative exponent means the top and bottom will flip and it'll become a positive 2. That would have also been a fine first step. Let's carry on. In fact, I think that's what we're going to do next here. I have a fraction raised to a negative exponent. So I'm going to make that a positive exponent, which means all the tops and bottoms switch with each other, right? A negative exponent becomes the reciprocal, the flip of the fraction raised to the positive exponent. The tops go to the bottom and the bottoms go to the top, and the exponent becomes positive. What's next? Well, I got a fraction raised to a power, and you might remember that we can just take the top of the fraction to that power and the bottom of the fraction to that power, like so. Now what? I have some multiplication raised to a power. So again, one of our laws said that you can raise each of those separate multiplied things to the power separately. The way we worded that was a product to a power is the product of the powers, which, if that language helps, great. If that just is more confusing, ignore it. You run that power of 2 through the bracket is another way to think about it. Okay, now let's just work all this out. 3 squared is 9. A power raised to a power. You multiply 5 times 2 is 10. And on the bottom, 2 squared, that's 2 times 2, 4. Whoo, so you see, right? We had all kinds of stuff there. We had some fraction reducing, including dividing with the same base, so we subtracted the exponents, put it on the bottom because more of them were on the bottom. We had a negative exponent to deal with. We had a fraction to a power, which meant we had to put the power on the top and the bottom separately. We had multiplication to a power, which means we had to separate that out like that. And then here, look at this. We even had multiplication, a power raised to a power. We multiplied 5 times 2. So we had like all but one, I think, of our exponent laws come up in some way in that question. I think the only one that didn't really come up, well, I guess the zero didn't come up, but also the multiplying with the same base, add the exponents didn't come up. All right, and this I already talked about. Yes, there's often more than one option, not necessarily right or wrong, just faster or slower. And the more you practice, the better you get at knowing what's going to be a better way to go. Okay, last topic for this section is something called scientific notation, which they tuck in here because it relies on exponents and exponent laws. But it's quite different, you'll see, than anything else we've been doing in this section. So, in science in particular, scientists started to find they were running into really, really big and really, really small numbers. This is, say, over the last, really only the last few hundred years for the most part. So in astronomy, we get really, really big numbers. So there's the distance from the Earth to Saturn. Here, on the other hand, in like quantum physics, we have really, really small things. Here is the diameter of a hydrogen atom, 0.00000000106 meters is how the distance across a hydrogen. And that's approximate because the electrons are swirling around. We don't need to get into chemistry. So scientists, you can imagine, got tired of writing all those zeros over and over and over every time in their calculations or, in their results or whatever it was. And so they decided to make use of powers of 10, because all those zeros there can be thought of as multiplying or dividing by 10, to create a shortcut called scientific notation. So let's look at this distance from Earth to Saturn again, 1,360,000 kilometers. Here is the process for putting that number into scientific notation, which saves you writing all those zeros. You put the decimal after the first non-zero digit. Well, in this case, the first non-zero digit is the first digit 1. So we put the decimal after the 1, 1.36. And then we count how many places did we move the decimal. The decimal was here, right? We don't see a decimal, which means it's at the end. The decimal was here, and we moved it all the way over to there, between the 1 and the 3. And if you count that up, we moved it 9 spots to the left. Now notice there's not 9 zeros, right? Because we moved it 7 zeros and then 2 more spots to get it after that 1. So it's not the number of zeros necessarily, it's how many places you move the decimal. That is how many times you need to multiply this number by 10, 1.36 by 10, to get 1,360,000,000. I feel like I might have said 1,360,000 before. If I did, I apologize. So we write it like this. 1.36 times, we could write times 10 times 10 times 10 times 10 times 10, 9 times. Of course, that's even worse than writing the number out. But we can also, how do you write 10 times itself 9 times? 10 to the power of 9. Yeah, so what that 10 to the power of 9 says is it's efficient way of saying multiply by 10 9 times. So the distance to Saturn is 1.36 times 10 to the power of 9 kilometers, which is better than all those zeros. This one only has seven zeros to add at the end, right? You can imagine when you get into numbers that have 20 or 30 or 50 zeros, you definitely don't want to be writing out those numbers with all the zeros. The scientific notation is a huge time saver. Let's try the same thing but with the small numbers. And the only difference is the exponent is going to be negative instead of positive, because remember, a negative exponent means 1 over, so you're dividing by 10 instead of multiplying by 10. So there's the diameter of our hydrogen atom again. Put the decimal after the first non-zero digit, which is that 1 right there, so 1.06. and then count. How far did we move? 1, 2, 3, 4, 5, 6, 7, 8 spots to the right. So we write times 10 to the negative 8 because we are creating a small number. So 0.000000106 is the same as 1.06 times 10 to the negative 8. And again, notice it's not the number of zeros, it's how many spots we move the decimal to make it after the first non-zero digit. If you're questioning why the exponent is negative, I sort of said this already. Remember that to get small numbers, we need to divide by 10 instead of multiplying by 10. And what is dividing by 10? Well, we could think of it as dividing by 10 over 1. How do you divide fractions? You multiply by the reciprocal. This is not something you need to do right now. This is just an explanation of why it works. And you could think of 10 as 10 to the power of 1. And what is 1 over 10 to the power of 1? Well, that is 10 to the power of negative 1, right? So that's why it works. Every 10 to the negative 1 is dividing by 10, which is exactly what we want to do to create a small number. So there's 2 for you to try. Put those into scientific notation using those 2 steps that we just learned. Okay, so 2 steps. The first step is we put the decimal after the first non-zero number, which in the first example there is an 8. So we put the decimal after the 8. So we have 8.235. By the way, you will notice that once things are in scientific notation, they are always in between 1 and 10, right? So 8.235. This one over here is going to be 3.9. They're never smaller than 1. They're never bigger than 10. So 8.235. And now let's count. We move the decimal from here to there, and if we count, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 spots to the left. So it is 8.235 times 10 to the power of 11. In other words, 8.235 times 10 11 times is this big number. Here we have a small number. Put the decimal after the first non-zero digit, which is a 3, so 3.9. And count. We move the decimal 15 places to the right to get it from here to in between the 3 and the 9. So we created a very small number, so it's 10 to the power of negative 15. In other words, 1 over 10 to the 15, so dividing by 10 15 times, gets you from 3.9 to this teeny number here. So that is putting numbers into scientific notation. You will also be asked to take numbers out of scientific notation. So let's try that here. 9.25 times 10 to the negative 7. So what is this times 10 to the negative 7 say? That says move the decimal left 7 spots. How do I know it's going left? Because negative exponent means it's going to be a teeny number, right? Well, if I move this to the right, I'm making a bigger number. I need to move it to the left to make a smaller number. So move the decimal left 7 places like so. The decimal was after the 9, right? See that there? The decimal was after the 9, and I moved it 1, 2, 3, 4, 5, 6, 7 spots, adding in the zeros as necessary. Why don't you try, I think, this one? Nope. I just gave you the answer. Okay, well, let's just do it then. 6.3 times 10 to the 4. So this is a positive exponent, which means it's a big number. Power of 4 means we're going to move it 4 places. So it was after the 6. I moved it 1, 2, 3, 4 places to the right. Again, adding zeros as necessary to fill those spots. So 6.3 times 10 to the 4th is 63,000. Okay, so so the last thing you'll have to do with scientific notation is do calculations, and we can do calculations without turning those numbers into their decimal numbers, which is a really good thing because This would have 35 decimal places over. This would have 22 decimal places over. These would be huge numbers. You actually wouldn't even be able to type those numbers into your calculator with all those zeros because the screen's not big enough. But we don't have to, because this says 3.3 times 10 to the 35 times 2.5 times 10 to 20. It's all multiplication, right? And we know that when we multiply, we can do it in any order we want. So let's take the two numbers and multiply them, and take the two powers and multiply them. And you see my little note here that you can skip this step. I just put it there so you can see what's happening. So 3.3 times 2.5 on your calculator is 8.25. When we multiply with the same base, what do we do to the exponents? We add them. So that's 10 to the 35 plus 22. 35 plus 22 is 57. Now again, you can see here why I say you can skip this step. I just took the two numbers and multiplied them, 3.3 times 2.5, and I took the two powers of 10 and added their exponents, 35 plus 22, and I get straight to my answer. Okay, so that is how you do calculations with numbers that are in scientific notation. You multiply or divide the numbers, and then add or subtract the exponents, depending if you're multiplying or dividing. There are some extra little twists that can come up there. If you get a number that is bigger than 10 or smaller than 1, you have to make an adjustment. I'm going to leave it for you to look at that. It doesn't come up very often in this course, but it is something to be aware of. That's our final answer. I got one more slide. What is it? Oh yeah, same thing with division, but you subtract the exponents instead of adding them. Okay, that's the end of this monster lesson, finishing our exponent laws and also talking about scientific notation.